Welcome to Math with Professor V. In this video, we're going to look at how to solve integrals that involve absolute value. So first, we're going to go to our building block. That is the piecewise definition of the absolute value function. So if you'll recall, we define the absolute value of x as follows. It's equal to x if x is greater than or equal to 0. And it's equal to negative x, or the opposite of x, if x is less than 0. And this should make sense because what it's saying is if x is greater than or equal to 0, basically it's already positive or not negative. When you take the absolute value, what do you get back? Whatever you started with, plain old x. If x is 0, 5, 100, when you take the absolute value, nothing changes. You get back what you started with. However, if x is less than 0, if it's negative, what happens when you take the absolute value of a negative number? It becomes positive. Well, what's another way of saying that? You take your negative number and multiply by another negative, and voila, it's positive. So this is our piecewise definition for absolute value of x. And you should have seen in your calculus classes, anytime you're working with limits and they involve absolute value or the derivative of a function, what you need to do is first rewrite the absolute value expression piecewise. Now, it doesn't always switch at 0. The domain split doesn't always occur there in your piecewise function. It depends on when the quantity inside the absolute value bars changes signs. So if you need to practice rewriting absolute value functions piecewise, I have a great video for you. It's one of the first ones I ever recorded, actually. And I'll link it here. Just click the top right. And it'll be in the description also. So I'm going to assume you've watched that video or you're comfortable rewriting absolute value functions piecewise. It's not super long, so if you haven't seen it, take the time to do that before we jump right in, because now, in order to evaluate integrals with absolute value, we're going to start off by doing precisely that, rewriting them piecewise. Okay, so first example, we have the definite integral from 0 to 2 of the absolute value of 2x minus 1 dx. So first things first, rewrite the absolute value expression piecewise. So we have absolute value of 2x minus 1. Similarly to absolute value of x, I'm going to have either 2x minus 1 or negative 2x minus 1 in my piecewise function. So 2x minus 1 for certain values of x, or the opposite, or negative 2x minus 1 for other values of x. How do I know where the domain splits or where it switches? It's not necessarily going to be at 0. In fact, in this case, no, it won't be at all. What you do is you take the quantity inside the absolute value bars, you're going to set it equal to 0, and we get 1/2. So 1/2 is where the domain's going to split, okay? So you have to figure out, should this 2x minus 1 go with values that are bigger than 1/2 or less than 1/2? And you can just test in your head. So pick something larger than 1/2, say 1. 2 times 1 minus 1, that's already positive. So taking the absolute value wouldn't change things. So 2x minus 1 corresponds with all values greater than or equal to 1/2. And then if you pick something smaller than 1/2, like say 0, right? 2 times 0 minus 1, that's negative. Absolute value makes that positive by multiplying by another negative. All right? If this was super confusing, then please go watch that video I mentioned a few minutes ago. Now, it doesn't matter which one you make inclusive, just don't put it on both, okay? Because at 1/2, it's 0. Positive 0, negative 0 is the same thing. So you just do what you feel. So now what we're going to do is look at our limits of integration. It goes from 0 to 2. Is this domain split at 1/2 relevant to us? Is 1/2 on the interval from 0 to 2? It sure is. So then we're going to come along here and we'll go, oop, we got to split you up. We're going to have to go 0 to 1/2 plus 1/2 to 2. Okay? Since our function is defined differently on each of those intervals. So from 0 to 1/2, I'm dealing with values that are less than 1/2. So I'm going to use negative 2x minus 1, which simplifies to negative 2x plus 1 dx, plus, and then on the next integral, which goes from 1/2 to 2, these values, these limits of integration fall in this portion of the domain where x is greater than or equal to 1/2, so we're going to use 2x minus 1. And as you see now, I just have two separate integrals to evaluate. They're pretty much identical. It's just one's the opposite of the other, right? One has an extra minus sign distributed throughout. That's all. Okay, so here we go. The rest should be pretty straightforward. We can just evaluate these directly. So antiderivative negative 2x would be negative x squared plus antiderivative of 1 is just x. This goes from 0 to 1/2 plus, and then pretty similar, this is x squared minus x from 1/2 to 2. And then now let's substitute in the limits of integration. So this is going to be negative 1/2 squared is 1/4 plus 1/2 minus, if I plug in 0 for everything, that'll be 0, plus upper limit of 2, that's 4, minus 2, minus, plugging in 1/2, I'll get 1/4 minus 1/2 now. So let's see, what does that give us? Negative 1/4 plus 1/2 is positive 1/4 plus 4 minus 2, that's 2. And then this is minus 1/4 plus 1/2. If I distribute the negative, then these 1/4s cancel. I just have 2 and 1/2, which is 5/2. Okay, how was that? Did you follow along okay? Good. Let's work on some more. I have plenty, don't worry. You'll be a professional by the end of the video. That is my hope. Okay, next one we have definite integral from negative 1 to 2, x minus 2 times the absolute value of x dx. So in this case, it looks like we have more going on, but inside the absolute value bars is just x. So you're just going to use that OG definition for the absolute value of x. Only look at what's inside when rewriting it piecewise. It's equal to x if x is greater than or equal to 0. Negative x if x is less than 0. So the domain splits or it switches at 0. Is that relevant? Look at your limits of integration. It goes from negative 1 to 2. Yep, 0's in between negative 1 and 2, so we have to split this up. If the integral went from 0 to 2 only, then I would just use this part and move on with my life, right? You wouldn't need to split it into 2. So here we go. We're going to go negative 1 to 0 plus 0 to 2. And then let's see. So from negative 1 to 0, we're dealing with values that are less than 0. So I'm going to replace this blue highlighted, including the absolute value bars, x, with just negative x. So watch, it's going to be x minus 2 times negative x dx. Are you all right? I replaced absolute value of x with negative x because from negative 1 to 0 on this interval, the x values are negative, so absolute value of x equals negative x. Plus, moving on, from 0 to 2, these limits of integration correspond with values of x that are greater than or equal to 0. So absolute value of x is just x. So now I'm going to have x minus just 2x dx. Good? Okay, don't integrate just yet. Notice we can combine like terms. Sometimes I have to remind my students to do that. And you always want to combine like terms before you integrate, you guys, because especially when you have limits of integration, then you'll have less places to plug them into, less chance of making a silly mistake. All right, and we hate silly mistakes over here. Negative 1 to 0. This is x plus 2x, so that's 3x dx plus 0 to 2, negative x dx. All right, not bad. Here we go. This is 3/2 x squared, evaluated from negative 1 to 0, plus, what is this guy? Negative 1/2 x squared from 0 to 2. And then upper limit minus lower limit, so that's going to be 0. Negative 1 squared is positive 1, so minus 3/2 plus negative 1/2 times 4 minus 0. So this is negative 3/2 minus 4/2 negative 7/2. All right. How was this one compared to the previous one? Easier or harder for you? I think rewriting it piecewise was easier, but maybe the idea, the setup was a little harder, huh? Let me know in the comments. Okay, let's spice it up a bit. Here we go. 0 to 3/2 absolute value of sine x dx. Ooh, so absolute value of sine x is a little bit harder to rewrite piecewise because if you think about it, shall I draw you a little baby unit circle? Sine is positive when the y values are positive. Yes, good. So that happens. Here's x, here's y. Here's 0, and here's pi. So between 0 and pi, sine of x is positive. 0 to pi. And then sine of x is less than 0 on pi to 2 pi. So from here to here. But then also it just keeps repeating, right? So you could say like plus 2 pi k plus 2 pi k, where k is an integer. Z means integers. Okay. So just be careful. If we're looking 0 to 3 pi over 2, okay, 3 pi over 2, that's less than 2 pi. So we're only looking at one revolution, but it's not as easy to write a piecewise defined function for sine of x, you know, because it doesn't just have one place where the domain splits. It's going to keep splitting infinitely many places. So as long as we just have an idea where to split it up from 0 to 3 pi over 2, we'll be good to go. Also, like, it doesn't really matter. I put brackets on this interval because I put the inclusive inequality here, and then this one was strict, so I put parentheses, so they matched. You could have it the other way around. It's totally fine. Okay, so do you know where 3 pi over 2 is? Here's 1 pi over 2. Pi is 2 pi over 2. This is 3 pi over 2. So we are going to have to split our integral. Sine is positive in quadrant 1. It's positive in quadrant 2. And it's negative in quadrant 3. So the split happens where? It happens at pi, yes? Okay, so let's summarize before we write it out. Sine of x is greater than or equal to 0 on 0 to pi. And then sine of x, you can just say is less than 0, or if you want to put less than or equal to, then just put brackets here, pi to 3 pi over 2. Okay, so we have to split it at pi. We have to split it at pi. So in the context of this problem, if we want to write a piecewise function for sine x, I'm not going to redefine it like for its entire domain. I'm just going to say only on the interval from 0 to 3 pi over 2, we're restricting it. Sine of x, it's already positive on 0 to pi. So that means taking the absolute value doesn't do anything. It's just equal to sine x if x is between 0 and pi. And then it's equal to the opposite of sine x if x is greater than or equal to pi and less than or equal to 3 pi over 2. So on this interval from pi to 3 pi over 2, sine is negative. So taking the absolute value makes it positive because it multiplies by another negative. So this is the way to redefine it piecewise. Again, if you want to switch this one and put it here, it doesn't matter. It doesn't matter, okay? All right, let's write up our integral now. So instead of 0 to 3 pi over 2, we're going to switch it at pi. Very good. So 0 to pi plus, and then we have pi to 3 pi over 2. So 0 to pi, we're on this interval. So absolute value of sine x is just sine x dx plus, and then from pi to 3 pi over 2, we have negative sine x dx. Good? Okay, so antiderivative of sine x is negative cosine x from 0 to pi plus, and then antiderivative of negative sine x is positive cosine x from pi to 3 pi over 2. And then now let's just plug in the limits of integration. So negative cosine of pi is -1 minus negative cosine of 0. So minus -1, that's +1, plus cosine 3 pi over 2 is 0, minus cosine of pi, -1. Oof, so many negatives to keep track of. Did you mess up or are you good? 2 plus 1. You should get 3. Yay. If you didn't, double check, see where you messed up. Probably you got it right though, yeah? Okay, nice. So sine, cosine, I would just treat them all the same way. So look at the interval and then just figure out where it's positive, where it's negative. Because it's very difficult to rewrite it piecewise like this. Sometimes I just skip this step. And if I know where it's positive, then on that one I leave it alone. And then wherever it's negative, I just add an extra negative if you don't want to do this step. Okay. All right, another one. Integral from 0 to 3 of the absolute value of x squared minus 4 dx. So when you're rewriting an absolute value function piecewise and inside is nonlinear, it gets a little more tricky. So I think the easiest thing when you have a little quadratic function like this is to just basically graph the zeros of that parabola. It's a parabola opening upwards, isn't it? And then you can really clearly see where it's positive, where it's negative. And I don't need a y-axis in this picture. This is a graph just to help me rewrite it piecewise. No one's grading me on my graph. Let me live and not put a y-axis, okay? So x squared minus 4. I'm just going to graph regular x squared minus 4, okay? The zeros are where? -2 and 2, yes? Is that clear to you? If it's not clear, you're just going to set it equal to 0. And then you get x squared is 4, so x is plus or minus 2. So here's my x-axis. It's a parabola opening upward. Here's the x-intercepts, and it's looking something like this. Okay? So notice on this portion of the graph and this portion of the graph, x squared minus 4 is already positive. So if we take the absolute value, and we're on this interval from -infinity to -2, or this interval from 2 to infinity, taking the absolute value won't do anything. It's already positive. When you take the absolute value, though, between -2 and 2, that's where the graph is negative. And what happens is it makes it positive. So it's going to flip it up like this. It reflects it. So if you were to graph absolute value of x squared minus 4, it would look like that. This highlighted stuff. So this should help us rewrite it piecewise. Watch. So I can say absolute value of x squared minus 4. Well, it's already positive. I'm just going to get back x squared minus 4 on 2 separate intervals. Okay, this is a little spicier. I'm going to get back the original here and here. Where were those? What is here and here? So that's where x is less than or equal to -2, or where x is greater than or equal to 2. Yes? Here it's already positive. That's from -infinity to -2. That's the same as saying x is less than or equal to -2. And then here it's also positive from 2 to infinity. Another way of saying that is x is greater than or equal to 2. Then I need the opposite of x squared minus 4, or I changed the sign, right? I flipped the negative values and made them positive if the x's are in between -2 and 2. So if we're in between -2 and 2, then I need to multiply by a negative. That's what the absolute value is doing. Good? Okay, perfect. Again, you can make these inclusive and these not. You can mix and match how you choose. Just don't double dip, okay? What I mean by don't double dip is don't put it here on -2 and then here again. Just pick one. All right, is this relevant? The domain splits at -2 and 2. Look at our limits of integration from 0 to 3. So I'm going to have to split it at 2. Okay, so we're going to go 0 to 2 and then 2 to 3, yes? So 0 to 2, that corresponds with, yes, x between -2 and 2. So f of x is, if you'll allow me, I'll distribute that -x squared plus 4 dx. And then from 2 to 3, that corresponds with x, greater than or equal to 2. I didn't mean to erase. So we're going to use x squared minus 4 dx. Good? Okay. Now, integration's pretty straightforward from here. So this is negative 1/3 x cubed plus 4x from 0 to 2 plus 1/3 x cubed minus 4x from 2 to 3. And then let's see, what do we get? So this is negative 2 cubed is 8 times 1/3 plus 8 minus 0 plus 3 cubed, that's 27 over 3 is 9 minus 12 minus 8/3 plus 8. Okay, so we've got two sets of negative 8/3, so that's negative 16/3, and then an 8 and an 8, that's 16, and 9 minus 12 is negative 3. So that's negative 16 over 3 plus 13, which is 39 over 3, and this gives me 23 over 3. Okay. All right, example 5, we have definite integral from 0 to 4 of the absolute value of the square root of x minus 1. Ooh, this one looks spicy. Don't worry, I got you. I'm here. So take whatever's inside the absolute value bars, set it equal to 0. That way you could figure out where your domain's going to switch, right? Where to split it up in your piecewise function. So set square root of x minus 1 equal to 0. You do this. That means rad x is 1. Square both sides, x is 1. So we're going to split our domain at 1. However, keep in mind it's not going to be x is less than or equal to 1 and then x is greater than 1 and that's it. Because x can't be just less than or equal to 1 indefinitely. Notice here we have square root of x. So we already are restricted. We can't plug in anything negative underneath that radical. So by default, x has to already be greater than or equal to 0. So if I say x is less than or equal to 1, that's cool, but don't forget to add on the other side, it also has to be greater than or equal to 0 for this to make any sense. Okay? Good. So absolute value, rad x minus 1 equals, so if you pick something smaller than 1, you take the square root of it, it's still going to be smaller than 1. Then you subtract 1, it's negative. Absolute value comes and makes it positive. So it's going to multiply by another negative. If you pick something bigger than 1, like 4, rad 4 minus 1, that's positive. So taking the absolute value doesn't do anything. So we're just going to get back rad x minus 1. Those commas were too far for my taste. Okay? So domain splits at 1. Is that important for us? Yes, this goes from 0 to 4. So we're going to split it at 1. Is it feeling repetitive? Good. That means you're understanding what's happening. So 0 to 1 plus 1 to 4. From 0 to 1, I'm working with this guy. So that's negative rad x plus 1 dx. And then from 1 to 4, just good old rad x minus 1 dx. Okay. If you need to rewrite these, go for it. So it's negative x to the 1/2 plus 1 dx. I know many of you are advanced though, so you probably do this in your head, but I'm just helping out in case some people are newer to integration and watching this as well. Okay, good. So we're going to add 1 to the exponent, divide by the new exponent. So adding 1 to 1/2, it's going to make it 3/2. Dividing by 3/2, I'm going to pick up a 2/3 in the front, and that negative, he's just hanging out, having a good old time. And then antiderivative of 1 is just x. This goes from 0 to 1. Plus, and then again, this one's going to be positive 2/3 x to the 3/2 minus x from 1 to 4. All right, beautiful. So let's see. This is going to be negative 2/3 times 1 plus 1 minus 0 plus 2/3 times 4 to the 3/2, that's square root of 4 cubed. So 2 cubed, that's 8. Minus 4. minus, now I'm plugging in 1, 2/3 plus 1. Okay, so I've got two sets of negative 2/3, so that's negative 4/3, plus 1 and 1, that's 2, plus this is 16/3 minus 4. And then look, these are just begging to be added together. They already come with a common denominator. So that's 12/3, which is 4, plus 2 minus 4 is 2. Voila. You guys, we're getting so good at these. Is there anything more difficult we can do? Yes. So the motivation for me making the video comes from yesterday's integral of the day. Yesterday being, in case you're watching this in the future. If you look up on the integral of the day playlist, it should be March 31st, 2024. If you're watching this in the far future, how cool. So this was the integral that I solved, except the limits of integration were different yesterday. I switched them so we can practice this whole idea of absolute value coming up, okay? So thought it would be fun. I'm going to spoil the surprise though and let you know that the way to start the problem is we're going to multiply numerator and denominator by the square root of 1 plus cosine x. So we've already solved this yesterday, but I will go through the steps again a little quickly. So rad 1 plus cosine x, top and bottom. And let's see. So now we have integral pi over 2 to 3 pi over 2. We have sine squared x radical 1 plus cosine x over the square root of, that is just the ugliest square root I've seen in a while. My apologies. 1 minus cosine squared x dx. So keep in mind, when you have conjugate pairs and you multiply them, you get a difference of squares. And the whole reason I want this to happen is because now I can use my lovely Pythagorean identity and replace 1 minus cosine squared x with, you got it, sine squared x. But this is where things get spicy. So we have integral pi over 2 to 3 pi over 2 sine squared x radical 1 plus cosine x over square root of sine squared x. And square root of sine squared x is not sine x. Oh no. Do you guys know what the square root of sine squared x is? Very good. It's absolute value of sine x. Okay. So we still have sine squared x here. And then we have rad 1 plus cosine x dx here. All right, very good. Now, how do we proceed from here? Well, you're going to look at the limits of integration. It's from pi over 2 to 3 pi over 2. Okay, let me just draw this out. We don't need the unit circle. We got it. Here's pi over 2. Here's pi. Here's 3 pi over 2. Absolute value of sine x is just going to be sine x wherever sine's already positive. So it's already positive here in quadrant 2 because the y values are positive. So over here, since sine x is already greater than or equal to 0, absolute value of sine x equals just sine x. Now, from pi to 3 pi over 2, maybe I should go like this to here. And then if I do different color, from here to here, sine of x is less than or equal to 0, so absolute value of sine x is negative sine x, because it's negative there, okay? So we're going to split this integral from pi over 2 to 3 pi over 2 at pi. And I'll just deal with each piece accordingly. So here we go. We're going to have pi over 2 to pi plus pi to 3 pi over 2. And then we have sine squared x radical 1 plus cosine x over, now remember, from pi over 2 to pi, sine is already positive, so absolute value is just sine of x. Here's the dx coming in hot. And then sine squared x rad 1 plus cosine x over, this time I need negative sine x. Good? Okay, then we're allowed to cancel and simplify and do all the lovely things that we need to do to finish the problem. So one of these signs cancels out, and then I'm going to take this negative and pull it out so that this is going to become a minus sign, okay? It'll make things nice, just you wait. So pi over 2 to pi sine x radical 1 plus cosine x dx minus pi to 3 pi over 2 sine of x radical 1 plus cosine x dx. And then the last little procedure you need to do to finish this problem is a u substitution. And we can use the same u sub for both integrals. So I'm just going to write it out once. We're going to let u equal 1 plus cosine x. And then du would be negative sine x dx. So negative du is sine x dx. And I also have to change my limits of integration. So for this first integral, u of pi over 2, I'm simply going to plug in pi over 2 for x, because these limits here belong to the variable of the integral. They belong to x. So it's going to be 1 plus cosine of pi over 2, which is 0, so 1. And then u of pi, that's going to be 1 minus 1, so 0. So the first integral is going to end up being, we have a negative on the outside because of this negative du, okay? And then the limits are going to go from 1 to 0, rad u du. So negative du is all of this sine x dx, okay? And then rad u is rad 1 plus cosine x. Okay, now let's look at the next little integral. Minus, so the limits are pi, 3 pi over 2. We already figured out pi becomes 0, so this is a 0. What about 3 pi over 2? So u of 3 pi over 2 is 1 plus cosine of 3 pi over 2, which is 0, so that's just 1. And then here we're going to have, this is rad u. And then do you remember what sine x dx was? Negative du. Oh, so I'm going to put du, and then since there's another minus sign, this becomes a plus. Are you okay? Yeah, you're fine. You're fine. Okay, one more thing I can do to make my life so easy. I'm going to flip the limits of integration here, and then that'll get rid of the minus sign. Remember, when we flip the limits, you multiply by a negative, so that'll make that positive 0 to 1 rad u du plus, don't I have the exact same thing twice? Oh my God, then why do two separate integrals? We're not going to, don't worry. This is 2 times the integral 0 to 1 u to the 1/2 du. Take the antiderivative, you have 2 times 2/3 u to the 3/2 evaluated from 0 to 1, which is just going to be 4/3. Okay, good. Now, a lot of the time when you'll deal with absolute values in integrals, either it's because they want like the total area between the curve and the x-axis, not the net signed area. They just want the total bounded area. So they don't want the negative area to cancel out the positive area. And then a very popular application has to do with particle motion. Okay, and so if you're asked for displacement versus total distance traveled, that's where this comes into play. Yeah. And I have a video lecture on this, so I'll link it for you guys if you're at that point. So when would we use an integral? If you're given the velocity function and nothing else, and you're on some time interval from a to b. If you want just the displacement, that would be the integral from a to b v of t dt. If you want the total distance traveled, then you need integral from a to b absolute value of v of t dt. Because basically the idea is whenever the particle changes direction, the velocity will change signs. And to capture the total distance traveled, you want to break up every time it changed direction so that you're not subtracting distance. So that's the difference when you're computing displacement versus total distance traveled given velocity. It always depends what you're given. So if you need to review that concept, then I have videos on that. But that's the most common place, where I've seen integrals pop up when you need absolute value. It doesn't happen too often. And it really doesn't happen often with indefinite integrals, but I just wanted to talk about it. So what about indefinite integrals with no limits of integration? How would you handle those? So I looked through the calculus books that we teach with, and there aren't any exercises. So we're just going to generalize based on our definition. So say we want to just talk about integral antiderivative of absolute value of x dx. I have no limits, right? So I don't know which part I'm working with. I just have to generalize and say, okay, this is going to be integral of positive x dx if x is greater than or equal to 0, and integral of negative x dx if x is less than 0. I'm just using my piecewise definition because I really have nothing else to go off of. And I'm going to have a piecewise answer as well. So you do each of them separately. So antiderivative of x, that would be, very good, 1/2 x squared plus c. That's if x is greater than or equal to 0. And then the other portion would be negative 1/2 x squared plus c if x is less than 0. And that would be your answer. Kind of weird. It really doesn't come up often, truly. If you wanted to do something a little more complicated, because, we're always looking to challenge ourselves. Say you had integral absolute value of sine x dx. So like I mentioned earlier, sine is positive from 0 to 2 pi, but then again from 2 pi to 3 pi, and then again from 4 pi to 5 pi. So there's a bunch of different ways you could write out a rule for those intervals, but it's a little messy. So I don't know. I would say what I would do is just say it's integral of sine x dx if sine of x is greater than or equal to 0. So like 0 to pi plus 2 pi k, where k is an integer, if you want to write that. And then it's negative sine x dx if sine of x is less than 0. So that would be, actually, if I put greater than or equal to, this one should be equal. My apologies. If this is inclusive, this should be included. And then sine of x is less than 0 if we're going what? That would be from pi to 2 pi plus 2 pi k. But I feel like this is not necessary. Sometimes I'll see it like this because everyone's just too lazy to write out rules, It's not very efficient. So what would we do? Just integrate each of those lonesome ones separately. So this is negative cosine x plus c. I'd say if sine of x is greater than or equal to 0, and then cosine x plus c if sine of x is less than 0. If you've seen it done differently, let me know. I'm curious. I really searched through all the calculus texts I have. There wasn't really anything. So if you have some reference or experience and you've seen it written more efficiently or differently, let me know. But that concludes the video. And like I said, the most important application has to do with particle motion and maybe some total bounded area. So that's why these are usually definite integrals. Always comes back to rewriting your absolute value function piecewise. That's the crux of it all. That's actually why I started my YouTube channel, because I couldn't find any book that explained how to rewrite absolute value functions piecewise in pre-calc or in calc. And somehow that skill needed to be learned and it was missing in that transition. So I thought, let me make a video so I can help my students out. And then things just grew from there, and I'm so grateful. So thanks for all your support. Subscribe if you aren't already. Give the video a thumbs up if you found it helpful. Comment down below. Let me know your thoughts, what you're practicing right now, what math class you're into. I'm curious if most of you guys are in Calc 1 or 2 who are watching, or is it just recreational viewers? That's also fun. And then if you need more in-depth lectures on integration or absolute value or other things, I have full video lectures for every single topic from pre-calc through calc 3. And they're all organized into playlists on my YouTube channel. So you should find it pretty easy to navigate. And you can also follow me on Instagram, TikTok, Twitter, Math with Professor V. Thank you guys so much for your support. I love you all, and I'll be back sooner than later. Bye.